So friends, welcome to you all in this Saturday Manufacturing Talks getting organized by the Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. So as usual, we are here because today is the Saturday, 8:30 p.m. and we are at the 15th, the week. We started our journey on the 13th of March with the beautiful lecture by Professor Amrit Mahotsav. And we are, very fortunate. In fact, I would say that our students, the entire audience, are very much fortunate that we are, able to listen to the eminent speakers from the industry, from the academics, on various topics of advanced manufacturing. The last week we had a webinar on the startups in manufacturing startups in India. What is the situation? How they can be mentored by the academic, the institute. And today we are, going to listen on a beautiful topic, which is the big data analytics. We all know this manufacturing, is striving towards the automation. And as we talk about the automation, that means more and more sensors are getting engaged, capturing the data from each and every step of manufacturing, each and every part of the equipment or the machine. So large number of data is getting generated to have a better insight about the process, about the machine also. Now the question is that how to analyze those, the huge amount of the data. How can we come up with a proper pattern out of the data so that we can have some decisive, the action. So on this topic, the big data analytics, which is very much pertinent to manufacturing, as I mentioned, we are going to listen to, from an eminent speaker, Professor Prasenjit Mitra. So I'd like to, read out his bios case. Professor Mitra is the Associate Dean for Research and Professor in the College of Information Sciences and Technology, and the Director of the Center for Socially Responsible Artificial Intelligence at the Pennsylvania State University in the US. His current research interests are in the areas of the artificial intelligence, big data analytics, applied machine learning, and visual analytics. In the past, he has contributed to the areas of data interpretation, data cleaning, and digital libraries, especially in tabular data extraction and citation recognition. Professor Mitra received his PhD from Stanford University in 2004, where he investigated issues related to modeling data and the semantics of data in an information integration system. Mitra obtained his Bachelor of Technology with honors from IIT Kharagpur in 1993. In 1994, he obtained MS in Computer Science from the University of Texas at Austin. From 1995 to 2000, he worked at the Server Technologies Division at Oracle Corporation as a senior member of the Oracle Parallel Server in the Languages and Relational Technologies Group. He has served as the consultant for several startups, including the board of advisors of Global ID. He was the principal investigator of the DAS project funded by the NSF Career Award. He has also been the co-principal investigator of the CiteSeerX, GameXSeer, and the ArtSeer digital library projects, the Regional Visualization and Analytics Center, and the GeoCamp Visual Analytics Project. Mitra serves as the director of the Cancer Informatics Initiative at Penn State. His research has been supported by the NSF, Microsoft Corporation, DoD, DHS, DOE, NGA, and DTRA. So with this, the bio sketch of the Professor Mitra. So we'd like to hear from him about the big data analytics concept and how that can be leveraged to the manufacturing to get better insight about the process, about the machine, so that we can really come up with a high throughput. Professor Mitra.
Yeah, thank you, Dr. Paul. I am delighted to be speaking here. The permissions to share my slides are there right now. It came back. So I'm going to share my slides right now. Okay, hopefully that is working.
Yeah.
And I can try to do that and move it. So, all right. Thank you for a very kind introduction and for inviting me to do this talk. I am a professor at the College of Information Sciences and Technology, and currently I am speaking from Colombia. I am serving as a Fulbright specialist visiting the University PUJ, Javeriana University at Bogota in Colombia. And I'm very thankful for the support given by Fulbright Colombia and ICTEX. So what I will do is I will talk a little bit about big data issues. And I do not directly do manufacturing. I'm a, as you heard, by training computer scientist, but I will talk about a problem that we are that we are working on right now in materials related research, which will give you an idea of what are the types of things that can be done. And then I will go into talking about work that we have done in big data analysis for data obtained from social media. And if time permits, I will talk about some work we did with chemists on chemical informatics. So I chose different applications to give a broad idea of the similarity you will see of the techniques across the different applications. And if you have a problem in additive manufacturing or any other manufacturing related problem where data simulations, computation can play a role, I would be very happy to talk offline and maybe perhaps even work together if the opportunity arises. These days with Zoom and so on, WebEx, whatever, we can communicate very easily. So I think I'm looking forward to long-term collaborations. So this will be a research talk. I will not go into too much of the basics. So big data analytics has been worked on for at least, let's say, the last 10 years, if not more. And there are some issues that I want to highlight that will be there in the rest of the talk, and pretty much in any effort that you undertake in this area. The first is the first issue that I would like to talk about. Good quality data, I don't have errors. So errors, some sensor measurement errors is one thing. Most of my sensors are working fine and the error is small. That is good. That's the first step. But even if you have, yeah, I don't know, control the shared content.
Prasenjit Mitra, you can switch off your video, and yeah, that may help the network problem a little.
You are having network problems?
Yes, yeah, slightly.
Okay, let me switch off the video. Okay, so now my video is stopped. So hopefully this is better.
Yeah, it's much better.
Okay. So as I was talking about, even if you have good data from your sensors, you have to understand the biases in your data. So essentially selection biases. So for example, in the West, in the US and so on, a lot of image processing where you're doing face detection is done on Western faces, so more Caucasian faces. And if you train a model and then you go and use the same technology in the general population, then the error, then you are trying the technology on a population on which it was not trained on, and there is more of a chance of errors. So this is, one thing about selection biases and user biases that can come in with respect to the data that we might need to be, aware of. For example, self-driving cars. If you are training only in good weather, then in bad weather, you don't know how it is going to behave. Of course, the car companies know better, and they are training in all sorts of weather, but the sensors don't work also very well when it is snowing heavily or even when it is raining heavily, and so more work needs to be done in those areas. The other issue is data locality. Data locality means that where is the data? Okay, so if the data is, can you get all the data? Now, especially when you have big data, all our data might not fit in the memory of a computer. So we would have to store it on disk and figure out a way of bringing the data in partially, doing some analysis, saving the results, and so on and so forth. So you might have heard of distributed systems such as Hadoop and Spark and so on, which allows us to bring in parts of the data and work on it. There is also an issue of privacy of the data. So what that means is that when you have, for example, in the US, there are reasonably strict laws due to which healthcare data cannot be shared that easily. And so hospitals need to make sure that our clinics need to make sure that the user's data is kept only at their locations and do not want to share the data. So in order to do big data processing, in that case, you have to move the computation to the location of the data provider. And that is what happens in what is called federated learning. So in this case, in federated learning, we have done some work on adversarial attacks on federated learning there's an ongoing project in my lab. But in federated learning, what happens is each of the hospitals, let's say, keeps their own data, but we send the computation to the hospitals, they do the computation, and then they send back essentially some weights, which is the weights of a neural network or whatever model we are learning. And that gets aggregated, and then again, it's sent back. So that's, in a nutshell, federated learning. That data locality issues are another big concern that you have to take into account if you're doing big data. Of course, velocity, which is that too much data coming in. So I work a lot on social media data. In that case, people are typing in things all across the world all the time. And you get, especially if it's a hot topic, you get a lot of data which comes very fast. So this is typically called streaming data. Same thing with if you have a large number of sensors, you have streaming data. And in a lot of these cases, you have real-time needs. So for example, if you have a lot of sensors and you're making decisions on real time, whether to move some piece of machinery, you have to decide within a limited amount of time. So you have to have computation that is efficient and online computation which gets back result in real time. Oftentimes, data availability is a problem. So this is sort of the opposite of the previous point. We have big data, we have too much data, lots of data, but then again, we have also data availability problems. And this is typically this is the cold start problem. So for example, we have done some work on recommendation systems. And let's suppose when a paper is written, if a paper has a research paper has 20 citations, you know what type of research community is citing the paper, and you know who is going to be interested in the paper, you know a lot more. But when a new paper comes out, it's hard to know. In the sense of papers, it's possibly easier in the sense that you have some content and you have to, you can decide based on the content what the topic is and so on. But this becomes a problem when you're, let's say, selling a new product. And you're building a recommendation system, all of a sudden a new product comes in, you do not know what to do, or a new movie that comes out. Okay. Now, you're in that case, the answer right now is mostly based on content and then using a little bit from the history and extrapolating. Another big problem is the semantics of the data. What does the data mean? What is the data telling us? We have to, at the end of the day, extract knowledge from the data and do something with the data. And understanding the data often depends upon the context and essentially the semantics, what is the meaning of the data. Interoperability means that the data might be coming from different sources and have different metadata. And if you want to mix data from multiple sources, you have to make sure that they are first normalized and processed. So for example, if you're getting it from two different sensors and they have slightly different ranges or slightly different calibration errors, if you just put them together without adjusting, the data quality will be hampered. So I have done a lot of work on text analysis. And in text analysis, as we know, natural language, the meaning of the words depends upon the context in which it appears. And therefore, context and semantics of the data is very important. So that's all I will say about sort of general issues in big data analytics today. In all of these, active research is being pursued. And anyone who wants to talk about it, I'd be happy to talk about it offline or work together if the opportunity arises. So now let me go on to the next slide. So I will, since this is a manufacturing center, I decided to talk about this project which just started last year on a seed project. This is being led by Professor Tarasankar Debroy, who is a leading scholar in the field of materials and at Penn State. And what we are trying to do here is use machine learning based quality improvement of additively manufactured metallic components. So what we are doing is roughly as follows. So I'm sort of the computer scientist, so I'm advising about and model the data and what type of models will give you the best results, things like that. But having worked with them, I've learned a little bit about the material science side. So there are about 5,500 commercial alloys, and only a small number of them are printed. And now what happens is when they are printed and generally in the manufacturing process, as you know, there are errors and defects. And if we can identify these defects early on, then we can either fix these defects or maybe throw out the material so that essentially the waste is minimized. The waste with respect to time taken, more materials that are used in the future processes and so on. So this shows some of the type of defects and that people have worked on. So what we were doing is a relatively straightforward application, but then we found some interesting things that we had to do. So what we did is we observed all the data that is available from the experiment, and we put it into the machine. Now, in modern machine learning, in deep learning, you do not have to do essentially what is called feature engineering. And so features are basically attributes of the experimental data that you're obtaining. And you do not have to do feature engineering. You can just put in the raw features, because the system itself, through the, a deep learning, the word deep means that there are many different layers. So in each layer, it is actually learning and creating something like features. And so it will, highlight or put more weight to things that are related to your output variable. So in this output, let's say in this case, the output variable was to detect the defects. And it would say, okay, these are the features that are useful to identify the defects. And so it will find the features and work with it. Now, all that is good, except that in our case, what we saw was that using these mechanistic models essentially improves our accuracy. So what I'm saying is that even though in theory the deep learning system should be doing the feature engineering. So in theory, we should not need feature engineering, but in practice, if we do some amount of feature engineering where we are using what we know from physics to create these more complex features than just raw observations, and then those are actually much more predictive of much more, meaning on the order of 5% or something, predictive of whether there would be a defect or not. And so feature engineering mattered. So in this case, this is showing what was going on. This is an example. So there's a real-time temperature measurement using IR camera, and using image processing techniques and so on. We detect the molten pool boundary based on the temperatures. And now then after that, we extract these features. So this is shown, this is sort of the theta, and this is the P. And so all of these points that are obtained, we are showing that in this case, 2 features. There were at least 6 or 8 sort of engineered features, and much more raw features that were used eventually in our model. So we extract the feature data, and then we train and test using machine learning algorithms. So this was supervised algorithm. So this is showing you a support vector machine that we used to classify abnormal conditions for defect formation. And the classifier was reasonably accurate, so it was giving over 95% accuracy. As you see here, there is an error. There is one blue thing, which there was no defect, but the way it drew the, in support vector machines, this is called the hyperplane, which is separating the blue dots from the red dots, that is separating the things that are without defect and the cases that were with defect pretty well. So some of this has been published in Nature review materials last year, and other groups have worked on, published in the Journal of Manufacturing Systems. And once we go ahead and print the component using these abnormal conditions, there are these defects that are there. So it's, so there are these. So what we have shown is that using mechanistic models and physics, and if you want to know the details, I'll be happy to send you the paper. I was part of one paper, and the group has written some other papers on it. And this is the part that we were working on. the defect formation, but there are many other aspects where machine learning can be used in material science, and it's being used rapidly, and that we know of. So this is sort of an overview of the work that we did, and shows you how what we call domain scientists, in this case, metallurgy folks, are working together. And we needed domain knowledge from the three disciplines. So in machine learning, we were trying to connect the process variables to product attributes using the available data. The metallurgists were working on connecting processes, the microstructure, properties, and performance. In these, the physics mechanistic models that were created were connecting the process variables to these product attributes via a mechanistic understanding. And as you can see, it has a whole lot of applications. Again, this is from the Nature review paper. So the uniqueness of the approach was that we were embedding the principles of physics in machine learning and improving the quality of the printed metallic parts. The printed metallic parts will have reduced porosity, lack of fusion and cracking, and we understand the hierarchy of the process variables and properties that affect the formation of defects. And we demonstrate a completely new path in metal printing that is economically attractive and does not require the trial and error approach. In the idea is that if we can do this in the computer, then we don't have to do it using real materials. At least in a lot of cases, we will know early on, or at least without spending a lot of money and time, what can work or what will work or what will not work. When you are, especially if you're trying to create new alloys and you want to figure out their properties or yields with respect to defects and so on and so forth, you can do that using computational methods. And this allows for the printing of more alloys by small, medium, and large companies. Now, of course, there is a lot of related work. Those are in our papers. So this is not something like totally new that we are saying for the first time, but we have done some of these applications were tried out and shown for the first time. And we have more work going on in this area that I'll be happy to talk offline. Okay. Now, so the second, I will switch gears now into a different type of data and show you something which is the type of work that is going on in essentially Snapchat, which has millions of users and is growing fast. And okay, so I have to stop the timer on this one. So it has millions of users and it's it's still growing fast. So the questions that we want to answer is, what is in this case, what we got is we got some data from Snapchat. And essentially my PhD student who has just graduated, Shanfang Tang, he went to Snapchat to do this work because the data could not be shared and could not be, because of privacy reasons, we could not get the data ourselves. So what we want to do is, is our understanding for user engagement is somewhat limited. So what we want to do is from the data, we want to find why is a user attracted by Snapchat? Will they be still active after 1 week or how long? What is the lifespan of this user? And why a user will still use the app next month? And maybe given 2 users who will spend more time on Snapchat. So we want to make these models and to answer these questions. And in order to do that, what we need to do is to understand the engagement of the users. So we'll talk about how we do that here. So the questions that we want to ask is, what is user engagement? And how to quantify the engagement of a user? What is the reason or the cause of the engagement of a user. So now there are challenges as to, how do you define user engagement? That, again, we want to define it with some application in mind. So downstream applications have to use this definition. And there are challenges in the data because the data is historical and that's heterogeneous. Things have evolved, platforms evolved, so there's a temporal component to it. And even the user's network, of course, evolves because they have friendship and actions and interaction. And how do we jointly model this type of data? People have done some basic work, but it was underexplored. So this is a paper that was published in KDD, the top data mining conference, knowledge discovery and data mining conference in 2020. And the other thing is what we want to do is we also want to understand the engagement of the user and to explain what is going on. Because a lot of machine learning models are black boxes where you give this and you get an answer. And unlike, let's say, regression models where you can go and look at the weights, although that has problems, you can at least get some idea of what is going on, or decision trees. A lot of neural networks are black boxes. But so in this case, what we wanted to do is we at least wanted to understand to explain how the engagement of the user is going on and what is going on. Okay, so the existing approaches were doing something more limited. So they were doing churn rate prediction. They were doing lifespan analysis, how long would the user be there, churn rate prediction, how fast, whether they would come in, how long they would stay, when they would go away. They were using user engagement prediction. So these were feature-based. So for example, based on demographic information, user activities, and so on, and some dynamic action graphs. These are works that has been done. But in this space, at least, although social networks have been used to do a whole bunch of data mining, in this space, the existing models, the related work are in our paper, they fail to model the friendship dependencies and ignore the user-user interactions when modeling user engagement. So either, they say, okay, A is friend of B, and that's it. But the time-varying nature of it and what are exact interactions going on between these people, that the finite granularity were not captured by these models, and we saw that they were important. Okay, so the engagement objectives may be different. One thing to note is the engagement objectives may be different across the apps and even across features. So for example, Facebook might be interested in how much time the person is spending on their site. Or Facebook might be interested in the number of clicks that people are doing on the ads, or just the number of clicks that people are doing on images or videos or so on and so forth. Whereas some other social network company might be more interested in just increasing the number of users, just increasing the amount of time, because they want to get people hooked and then perhaps do things. And even if you look at different features, so on the friends page versus the camera versus the discover page, when you knew like a recommendation. So the engagement definitions need to be different in these, and the objectives are different. Okay, so that has not been taken into account that much. I already mentioned that we need the answer why, and because machine learning often is a black box model, and this work was done in collaboration with Snapchat, and Snapchat, of course, for business reasons, wanted to understand what is going on. So our approach was that we define what is user engagement, and I'll give you a high-level idea in the next few slides, using what is called the expectation of metrics of interest. We want to quantify the engagement, which means we propose an end-to-end deep learning framework using the historical data to predict the engagement. And again, we want to find explanations as to why this engagement is happening. And we have like 5 different explanations. So the first one is the first thing that we are talking about now is user engagement. So what we do is we divide the time interval into roughly equal continuous time intervals, equal length. We have the friendship, which is the social network on Snapchat. I'm sorry that the images got moved around in the presentation, but anyway, we can't do much now. So so this is sort of the user, and then you have these interactions. This says GU, the user graph at time t, and this is not the same user graph at time t dash. So this is capturing, this is a dynamic user graph, this is capturing the time variation. And so we have the nodes, the edges, the node features, and the edge features. So this we wanted to capture the user interaction, so the direct communication between friends, and we wanted to also capture the user action, which is what is the user doing in the app. So this is not with another friend, but this is maybe writing something or posting something, excuse me, or clicking something or reading something. So that's what user action is. Okay. So we propose to use the expectation of metrics of interest. So the intuition is that the users are more engaged, who are more engaged, tend to be more active and or contribute more. And we want to have flexibility. The metrics can be selected according to scenarios or different apps or different platforms. It has to be dynamic. There has been a lot of work on static social networks, but in this case, the social network is always changing and the users are engaging in actions. And it has to be clear to understand. So the engagement is defined as the expectation of this MUT, where essentially it's this MUT can be defined differently based on your application and your needs. So it can be the session time, how much time the person is spending. If you are interested in revenues, then you see how many clicks they are making and so on. So the framework is flexible. You have to plug in the metrics that you are trying to optimize. Okay. In order to explain the user engagement, we have the user action importance. So now this will be, all of these are, you think about this as feature groups. So these are metrics that will be learned using our data. So we are in a supervised learning setting where from the data and looking at users who spend more time or whatever other who click more ads, we will figure out which user actions are important and how much. So this assigns each user action a score and tries to reflect its sort of weight and importance to the user engagement. Similarly, we have temporal actions, and temporal importance is to identify the importance of some user activity at each particular time interval. So the idea is that the same action at different time intervals can have different weights, and different time intervals might be differently important in order to predict future user engagement. Obviously, recency is an important feature. So something that I did 1 year ago might be less important than what I'm doing now. Friendship importance, which characterizes the contributions of friends to user engagement over time. And some friends are more important than others, but overall, just having some amount of friendships might be important for people to be coming back. So those are the individual user engagement features or feature groups that we are interested in. But there is also an interest in understanding at the global level what is going on. And so the reason is that we cannot create individualized apps. So in an app, we have to take some action. So for example, you build a feature in the app and you have to do A/B testing. You have to find out whether this feature is useful for the at least a group of people, if not for the whole set of users. And based on that, you say, okay, how do I optimize that? So in this case, what we are looking at is global user action importance and global temporal importance. Okay. So the explainable, we want to do explainable engagement prediction. So we are building a framework where for every user, we are predicting the engagement score with these explanations, AU, TU, FU, that were defined in the last few slides, and based on the historical user graphs. And we want to generate the global explanations too. All right, so how do we, so that was what is user engagement. How do we quantify the engagement of a user? So this shows you roughly the architecture. So at the bottom level, what we have is we have the friendship social network and we have the interactions that are happening. And using these graphs, we employ essentially graph convolution networks, GCNs, to do graph encodings. So these are representations of whatever these graphs are that we are obtaining. And again, this is over time and over different groups of users. And then we do, so this is over different groups of users. Then at this point, we do the temporal module. And in a lot of these cases, we are using what is known as an attention mechanism. And the attention mechanism, I'll go to the next slide, explain it, and then come back. The attention mechanism, this gives you an example to show what the attention mechanism is. The attention mechanism model, which is a famous paper 3-4 years ago from Google, which says attention is all you need. It possibly has over 1,400 citations now. What it is trying to do is it's trying to say that all words in a sentence, in this case a sentence, are not equally important. So you need to put more attention on certain things in order to get the semantics. And what this slide is showing is that for each of these words, it is showing, what, where the attention is. We are processing from left to right. So initially, when we say FBI, there's only one word before it. So it's just, attention goes to the FBI. But when it goes to is, then, if you think about it, who is chasing a criminal and so on, who is doing this? The FBI is. The word FBI has more attention than the. And then if you look at the word chasing, then it becomes FBI is chasing. And then if you look at and so on, you see the attention. So criminal. So this, this person is a criminal and is being chased. The attention is there, and so on. And then when you have the whole sentence, then a criminal is on the run and is being chased, and then and so on. So the attention model, in general, the basic idea is that it tells us which parts of the sentence, which words should we pay more attention while trying to interpret the semantics of a particular word. This has been applied to image processing. Actually, one of my students worked on looking at X-rays and CT scans of the lung. And the attention model, in a way, gives you some explanation that artificial neural networks, especially in deep learning, were a black box and it was not very explainable. Using the attention model, what we found in looking at the X-rays and CT scans of the lungs was that there are different patterns that are correlated with these different diseases. So for example, with COVID-19, our model said pay more attention to the bottom parts of the lungs. And we had mixed in data from patients who are suffering from COVID-19, as well as from pneumonia, and as well as from the common cold and flu-like symptoms. And then in the case of the pneumonia, they found they said more attention towards the middle part, and in abnormalities or buildups, and in flu-like symptoms, it was more in the top part. Now, this was one result. There have been about 45 other studies, and all providing different, some different understandings. And together, I think the community has some reasonable understanding of how machine learning can be used to analyze X-rays and CT scans and identify COVID or see signs of damage in the lungs that are related to COVID versus other things. Okay, so that aside, so this is the attention, this is a brief primer on the attention model. And what we want to do here is, so what is our attention here? The attention here, if you think about it, is on the friends modules, excuse me, and I'll go into it a little bit more detail. All friends are not equal. So I think I have the slide here. So in the friends module, if you look at the chat rate and the snap rate, among your friends, what % of friends do you communicate with? So there is a small subset of friends, those are your close friends. And less than 20% of your friends you're chatting with or snapping. And those are the friends that we should provide more attention to. So the attention model is picking and choosing which of the friends to give more attention to in the graph. So that's why we are using the attention model and how we are using the attention model here. Okay, in the temporal part, it's the same thing. Which time span should we pay more attention to, and so on. In some cases, it might be that, well, you know, if I'm trying to figure out whether I'm sick today, or whether someone will come today or not, maybe, okay, if I was sick yesterday, there's a high chance I'll be sick today. So just that, you know, recency matters. But in some cases, maybe some periodicity matters. So if I go hiking every weekend, the fact that, you know, maybe what I did last weekend is more important to predict, and what has happened during the week is not that important. So the attention model is used to pick up which days in the past or which time periods in the past are most important to do the user modeling, and so on. So we put it in a deep learning framework. I'm maybe running a little short of time, so I'll move a little faster here. The temporal module uses what is known as a LSTM. So this is a RNN, where each time it's like, you know, LSTMs and RNNs are used to model sequences because essentially they have the temporal aspect, the sequence aspect of one event or one event happening after another, and so on. All right. So in the friendship module, we use a tensor-based GCN, and the tensor, instead of a matrix, we have, you know, the other dimension is basically we combine our features into different groups. So you can put all the features together, but then it's hard to interpret things. But then what we did is we combined our features into different groups to say, okay, this is the user snap information, snap related features, and this is the user's chat related features, this is the user's posting related features, and so on. Then we got better results, and we know which group of features helps the most. So I've talked a little bit about the temporal module. This is neural network machinery. When we want to do prediction, we have introduced 3 latent variables, which is the friendship attention, the temporal attention, and the user action attention, which user actions are more important than others. And we have the node embeddings. These are the representations that we get from the graphs. So the node embedding is the equivalent. You might have heard of word embeddings like word2vec and so on for text. The node embeddings are similar representations. hopefully semantically important representations of nodes in a graph. So that's how we model it, and then it's learning from the data to figure out what these probabilities are, to figure out what these attention models should be. Okay. So in the interest of time, these are all laid out. The math is laid out in the paper, and I will skip that. And I'll show you a little bit of the experimental results that we have, and maybe then we'll see how much time we have. So each data set is constructed from all users that live in a different city. And we used cities from 2 different continents. So 2 definitions of engagement were used, which is the user session time in hours and the SNAP-related activities. We used a whole bunch of baseline models: linear regression, XGBoost, MLP, perceptrons, LSTM, state-of-the-art RNN model, GCN, which is the graph convolutional neural networks, and then our model, which is temporal, GCN, LSTM altogether for engagement prediction. And no, the temporal GCN LSTM was also a base model. Ours is the FATE model, which uses all of them, and basically that was described in the previous few slides. So we used root mean square errors, mean absolute errors, and so on. And in all the cases, our model was better. And if you are thinking as to the computational complexity, our model was actually also faster. And the models are a little bit more complex, but the reason it's faster is because it's actually doing a lot of pruning early on by looking at some of the lower granularity data, and by looking at some of the features that have been designed, and so that's why it's also faster. All right, so now, as I said, we wanted to look at these models and say that it needs to be explainable. And so we got these action importance scores. Our task 1, remember, is to infer how long they will be there. And task 2 is to infer SNAP-related actions, whether they will send snaps and so on. So obviously, in these 2 cases, as you can see, the session time is quite important in task number 1, and the snap send and snap view interactions are quite important in number 2, and we see all the others are more or less about medium. And we looked at users who have different sort of engaging behavior. So there are snappers. Think about it as maybe producers and consumers. So there are these snappers, and then there are the discoverers. And these were not, this we detected from the data. In this case, the individual importances. So in the snapper case, essentially snap sending and viewing was the more important feature. In the viewer case, the amount of time they are spending in the public discovery feature. So these are explorer, as you see, either public one or in the friends one. So these are the recommendation systems, or in the story views, and so on and so forth. So it's actually getting things which make sense. We plotted the temporal importance and so on. This is the global temporal importance, and that gives us some ideas and pictures of what's going on. We have obtained individual user temporal importance, so that allows us to understand the nature of interaction of each individual differently. And then, so once you know that this is a chatter and this is a watcher, you might decide to present the screens differently. In the sense, in the watcher's case, you might provide more content that they can discover, and in the chatter's case, you can possibly provide them. You don't have to worry too much about the discovery part, but give them the opportunity to chat and send. We found, we looked at the friendship importance, and not surprisingly, users have similar, users with have similar session time behaviors, and this is similar to their most important friends, and you see that there are session spikes, which are also in line with their friends, of course, because they have to interact. And we have, we did some explainability. Sorry, this should not be expandability. This should be explainability, explanations with respect to some of our baseline methods, and found that it was quite interesting. I think I have run out of time. I can stop there and take some questions, and I have some more slides. But if there is time, I can go into those, and so on. So
yeah,
okay.
Yeah. It's okay. I mean, you can, if you have got 1 or 2 slides more, you can show that, and then we can come back to the question and answers.
Okay. So I will then keep going. Yeah. So in this case, what I want to show is, so we did some work with research data, which is basically.
Professor Mitra, we are unable to see your slide.
Okay.
You need to, I think you have come out of that, so you need to share your slide.
Can you see it now?
It's coming up, I believe. It's coming.
Can you see it now?
Yes, sir. It is visible to
Yeah,
us.
it is there.
Yes.
Okay. So, so I've worked on research, and one of the things that I wanted to mention with respect to big data analysis is the importance of good principles for metadata. So metadata describes the data and is very important. And there is this set of principles called FAIR principles. And you can go to the website listed here. So FAIR stands for findable, and I'll go with the AIR. So in the findable is that if you are using data and reusing data, it should be easy for people to find the data. And so if you can assign some identifier, hopefully that is globally unique, the data needs to be described in rich metadata and so on, then the data is much more usable. Accessible is that when we find the data, we need to know how they can be accessed, and including authentication and authorization, and essentially the metadata has to be retrievable using these identifiers, and hopefully using a protocol that is open, free, and universally implementable, again allowing for authentication and authorization, and so on. I is interoperable, so that means that we need data with other data, and using that we want to interoperate. So we need to make the metadata use like a formal knowledge representation language using which we can share the data and the metadata so that they can be used readily, and use vocabularies that follow FAIR principles. If people are calling the same thing different things, it's very hard to know what exactly they're talking about and to put data together. And the last one of R is that we want to optimize the reuse of the data. Again, in this case, the metadata needs to be well described so that they can be replicated and combined in different settings. So, why do we want to do that? Of course, in research, if we share the data, then we can integrate data from different places and see, okay, if I'm working on pollution data here and somebody is working on pollution data in India and in China, and we can all share our data to do really big data analytics across the system, then data sharing is quite important. So we have done some other projects.
Hello. Hello, Prasenjit Mitra.
Yes, sir. You are audible.
I think he is not audible, no?
No, sir. I think he has lost his network.
Last few days, the network is really, especially maybe today because of the rain. So, friends, by the time Professor Mitra, they rejoined. So, if you have got any questions, you can put it in that chat box. Ranjan, I think now he is.
Yeah, he's back. I think.